SignalShark, 7 senses for signals.
Can you find the difference? We can measure it, and this video will prove you how easy and fast that can be. Whether as consumers or as network operators, service providers or as a regulator, we nowadays understand properly working and well-performing cellular networks as a must. As a consequence, poor reception, bad speech quality, low data rates, or a bad quality of service in general can threaten business models significantly and risk uprising applications in the domain of ultra-reliable or high-throughput communication, IoT, or, for example, car-to-car communication. In today's mobile cellular networks, the quality of service can be verified remotely by network operators in the Operation and Maintenance Center (OMC) or the Operating Support System (OSS). The OMC provides various key performance indicators, also called counters, telling if an individual base station or multiple cells work properly. Two very useful counters are the call setup success rate (CSSR) and the traffic channel drop rate. In the OMC, these two counters are typically displayed in diagrams over time. The call setup success rate, or CSSR, presents how many calls or connections can successfully be established between the user equipment and the base station. This value is measured in percent and typically ranges above 95%. Lower CSSR values mean worse quality of service and hindered problems in the mobile network. In the shown example, we assume a base station with 3 antennas or 3 sectors. For each sector, the base station's OMC can provide the CSSR value, which usually reaches 100% or slightly less. In our example, however, after 2 days of perfect operation, CSSR values degrade for sector 1, blue curve, and slightly for sector 2, orange curve, while sector 3, gray curve, remains unaffected. The blue and orange curves in the diagram for sectors 1 and 2 not only show temporarily degraded CSSR values, but they reveal a daily periodicity. We will focus on this issue again later. Apart from the call setup success rate, another essential counter is the traffic channel drop rate, or TCH drop rate. The TCH drop rate indicates how many established connections between the base station and the user equipment have been dropped. Typically, the TCH drop rate ranges near 0%, as visible in the shown example, for all sectors up to end of day 2. In contrast, from day 3 on in our example, for sector 1, TCH drop rate increases to a value of up to 7% each morning around 6 o'clock, while for sector 2, we see just a slight increase in TCH drop rate, combined with the same daily rhythm. Many OMC systems provide further details to the TCH drop rate, such as uplink or downlink power levels and quality indicators. Based on the information on the CSSR and the TCH drop rate provided by the OMC, network operators urge for troubleshooting in order to quickly improve the quality of service. In general, problems in the mobile network can have internal or network external reasons. Speaking of external interference basically means other non-desired radio signals interfering with the user and the network. We will lay our focus on this interference type for the rest of this presentation. External radio interference can take numerous appearances. Old, faulty, non-EMC compliant electronics, signal repeaters, jammers or transmitters with the wrong frequency allocation represent just a small extract of sources for non-desired radio signals degrading mobile networks. The more the electromagnetic spectrum densifies for radio applications, the more increases the risk for interference issues. Looking back into the OMC, we could see different and partly periodic curves for the CSSR counter for 3 sectors at one base station. As a reminder, the CSSR presents how many calls can successfully be established between the user equipment and the base station and typically ranges above 95%. The CSSR may drop due to external radio interference, blocking cell phones from properly connecting to the base station. Such interference does not need to affect an entire base station equally. As shown in the example, the interference affects Sector 1 severely, Sector 2 just slightly, and Sector 3 not at all. This is mainly due to the location of the interferer and the alignment of the base station antennas. In our example, we could also see periodic CSSR curves for Sector 1 and 2. Typically, this hints at interference from sources passing by, like delivery trucks, or from sources being used with a certain rhythm, like a faulty microwave being switched on every morning around 6 o'clock. Based on the information provided by the Operation Maintenance Center of the base station, we were able to notice problems in our mobile network. Also, we could tell that external radio interference might be linked to these problems. We are even able to narrow down the source of interference to a specific cell or a sector. As a consequence, the next task will be to actually find the interference in question. Starting an interference hunt is never easy. Many times we see ourselves not only confronted with technical challenges, but with organizational challenges too, which distribute over multiple phases in our hunt. From where we start an interference hunt, the signal of interest will most likely be very weak and unstable in power and possibly even in frequency. Moreover, signal reception will underlie reflections and an increased noise level, especially in urban environment. As a conclusion, we can differentiate between multiple challenges related to the signal properties and related to the reception conditions. In addition, we must consider organizational issues or working conditions for an interference hunt as well. This may cover our obligation to documentation or that we are just on our own and don't have a helping hand. Based on an exemplary interference hunt, we will address the mentioned challenges on the following slides phase by phase, showing that SignalShark turns out to be not just a spectrum analyzer, but your third hand when it comes to any radio issue. Starting the interference hunt, we first need to set our system up. It consists of the SignalShark base unit and the automatic direction finding antenna ADFA1. Setting the automatic direction finding antenna up cannot be easier. With its non-penetrating magnetic mounting plate, the antenna becomes mission ready on any usual vehicle, also rental cars, in less than 10 minutes by one person. Even though the magnetic mounting plate is easily removable, its adhesive force allows speeds up to 130 km or 80 miles per hour in combination with Norda's Auto DF antenna. Nevertheless, an antenna fixing belt and a foam protector around the antenna's hybrid cable provide additional safety and comfort. After connecting the antenna to the SignalShark base unit in the vehicle, our system is set up. Another computer is not necessary, as SignalShark includes both receiver and computer. Hence, we're now ready to take a closer look at our signal of interest and how we can initially detect it. As mentioned, in the early phase of signal detection during an interference hunt, we are confronted with many challenges at the same time. As the interfering signal type, meaning its specific frequency and bandwidth, is normally unknown, we typically need to scan the affected frequency band looking for any suspicious signal. a spectrum analyzer as SignalShark with high sensitivity, high real-time bandwidth, waterfall and persistence display allows us to determine the correct center frequency, frequency span and resolution bandwidth much faster compared to soul-swept or scanning analyzers. However, this has limitations, particularly when starting the interference hunt at ground level in urban environment. In such urban ground level scenario, the chance for initial signal detection is very low because of the increased noise floor caused by all the electronics in the environment, but also because of multipath propagation conditions. It can then be useful to take measurements from the typically elevated spot of the affected base station, meaning on a rooftop or even a tower. Even that bears pros and cons. The pros are that we can avoid the added noise from ground level, that we increase the chance for a line of sight to the interference, and that we overcome attenuation by infrastructure. The cons are just as important. Accessing a rooftop with base stations on is often difficult for organizational reasons and may sometimes be not possible at all when it's just needed. Moreover, when taking measurements close to other radio transmitters, especially when they are intense like a base station, the risk of overdriving the measurement device increases severely. Overdriving a spectrum analyzer will lead to harmonics and spurious, which forbid reliable measurements. The scenario that we have currently set up virtually is in fact one of the major challenges or dilemmas in interference hunting. At ground level, the signal in question may be too little, and on rooftop other signals around are too strong. The classical answer to this is the use of additional RF hardware such as preamplifiers and bandpass or bandstop filters. However, even these measures bring pros and cons. On the other hand, with SignalShark, interference hunters can overcome the interference hunting dilemma a little further. SignalShark is not only extremely sensitive, in the telecom bands its typical noise figure ranges around 12 dB without a preamplifier, but it also provides an enhanced dynamic range due to its built-in sub-octave filter bank. This bank of band passes leads to impressive dynamic values, which are typically 40 dBm for the IP2 and 14 dBm for the IP3 in the telecom bands. Considering SignalShark as a compact, versatile spectrum analyzer and direction finding system, this combination of high sensitivity and high dynamic range is not a step but a leap forward and will prove itself in the following scenes. In our exemplary session, we simply focus on a 2G base station. In real-time spectrum, we activate multiple traces to evaluate min and max levels. Activating spectrogram and persistence view allows us to analyze the spectrum even better. Now we can adjust our settings, such as the span and the measurement time, to further focus on the signal of interest. Such analysis, with various views onto the signal and possibly corresponding demodulation, is an important helper to conclude on the eventual interference source, and it also increases our experience to better deal with future interference issues. Typically, interference by faulty electronics behaves fluctuative and doesn't show any clearly limited bandwidth. In contrast, intentional radio signals, which act as interference, can typically be identified by a systematic signal pattern due to modulation scheme, bandwidth limits, and channel access. If urgent help is needed, SignalShark can even be operated remotely. Based on its Windows 10 operating system and its USB interfaces, you can simply use an LTE stick to connect to the internet. By that, it becomes possible to establish a remote desktop session and have an expert not only looking at the same display, but even taking remote control of the device in the field. This workshare allows much more efficient resource planning, particularly in field service, where interference hunting depicts just a small portion of daily work. Based on the present analysis, here by real-time spectrum view, waterfall and persistence in parallel, we activate SignalShark's automatic direction finding mode. In Auto DF mode, we typically use 3 views: real-time spectrum, bearing and map view. These 3 views can also be initiated and automatically configured based on SignalShark's various measurement setups and presets, which cover various signal types and environments, such as urban or rural. Of course, adding new setups and modifying settings based on a preset to individual needs is possible. In our scenario for spectrum view, we use similar settings as before to visualize our signal of interest in the best possible way. Here as well, we can use markers and traces to indicate, for example, other radio signals in adjacent channels or to measure channel powers. In bearing view, the major setting which needs to be adjusted to the signal of interest is the channel bandwidth, CBW. It needs to be set to the signal bandwidth, now indicated by blue markings in the spectrum. Choosing a wider CBW can be useful when the signal changes in frequency, but such wider CBW also adds more noise power, which we want to avoid. Choosing a smaller CBW can be useful when signals in closely adjacent channels are present and should be excluded from localization. However, smaller CBWs also mean lower received power of the signal of interest. Hence, the CBW setup is an important parameter which should match to the signal in question. Based on the currently visible setup, now already, SignalShark takes dozens of bearings. In bearing view, we see the current RMS channel power for the channel marked blue in spectrum view. In addition, in bearing view, we also have indicators for DF quality and elevation, to which we will come later. Apart from the compass rows showing us the latest bearing result, we see one orange and one black dot. Whenever a valid bearing result has been calculated, these 2 dots switch in color and the 3 bar graphs will be illuminated in orange color too. Upon a valid bearing, also a red line in map view will be displayed for a short moment. In map view, we use the preset city as we consider our route and suspected interference in that environment. SignalShark's maps are offline maps, which can be downloaded to SignalShark or to any connectable other storage media for individual geographical areas and zoom levels. Based on the explained settings, we start our drive. SignalShark will start creating a heat map with help of each valid bearing that it took while driving. Non-valid bearings will be ignored according to our preset squelch, stability and DF quality settings. The stronger the signal becomes and the more line of sight events can be received, the better are the chances for quickly narrowing the interferer down on the heat map. Also, the driving route plays a significant role to reach soon success. The route should never be just straight, but it should make curves or even circles around the suspected area. By that, the SignalShark's 3-dimensional geolocation algorithm will be provided with even more useful bearing data. The video shows the great advantage of such automatic system. In contrast to manual bearings, where we have to get out of the car, take a more or less accurate bearing, find the next useful spot, take the next bearing and so on, we can now simply drive around and SignalShark will automatically process the localization result based on more bearings than we could ever take manually. Due to the sheer amount of taken bearings, we overcome fading effects and reflections, and the statistical chance for locating the source of interference successfully rises significantly. And, last but not least, with this system we can remain seated in our vehicle, don't lose time with getting in and out, finding the right measurement spot, and we can do so even under bad weather conditions, whether heat, snow or light rain. In an option, SignalShark can be connected to a navigation system, so that a single person doesn't need to look at the SignalShark display to get a direction indication, but he or she can simply be guided by the navigation system, which is fed by SignalShark's latest localization result. SignalShark also allows for connecting another display, even touch display, via HDMI to improve work with multiple persons and to leverage trainings. Getting closer to the signal source, we must bear in mind that it could also be located somewhere on higher levels or in hills or mountains. This is where we have to remember SignalShark's ability to evaluate not just azimuth but elevation too. SignalShark's ADFA has effortfully been calibrated in a three-dimensional environment. It is able to determine elevation angles between -20° and +40°. For techies, it is essential to understand that the antenna's correlative interferometer principle evaluates the azimuth and elevation angles based on one and the same three-dimensional covariance vector, which will be correlated to the reference database with its permanently stored 3D calibration data. Hence, next to the azimuth angle, the elevation angle too is the result of a traceable mathematical process which is actively taken into account for direction finding. This leads us to important advantages of SignalShark's auto DF antennas. Azimuth and elevation results are statistically sovereign and reliable. Localization accuracy is increased, and bearings towards elevated signal sources can truly be processed. In urban environment, we can observe that interference hunts by vehicle often lead to good localization results within the first 10 minutes. While approaching the signal source, it is not uncommon to observe the signal increasing by more than 100 dB over an air distance of 400 meters in the telecom bands around 2 GHz. Arrived at the point of interest, we disconnect SignalShark from the auto DF antenna, take an adequate directional antenna and proceed the last few meters on foot. Note that our suspected area in this case has a width of approximately 50 meters. Even so close to the signal source, taking bearings with directional antennas on foot, particularly in urban environment or in buildings, can be tricky due to reflections and shadowing. It is hence recommendable to first target SignalShark's localization result before following up on other traces. Bear in mind that SignalShark's localization result is based on hundreds or thousands of bearings from different spots. Also note, if the interference source is located on higher levels of a building, signal strength will most likely drop when approaching that building on foot due to shadowing effects. Hence, when targeting SignalShark's localization result on foot, sweep your directional antenna not just over azimuth, but over elevation too. With SignalShark's modular antenna system, consisting of the automatic DF antennas 1 and 2 and the 4 different handheld directional antennas, you have a great chance to find any interferer in a timely manner. In the end of many interference hunts, we usually need to create a report on our findings, mentioning the interference frequency, the maximum detected signal power, and of course the suspected or determined location of the signal source and, if possible, the source itself as well as its operator or cause. With SignalShark you get great means of documentation even automatically. During the entire drive, SignalShark's Windows 10 operating system allows for running a display record software in the background that particularly offers huge benefits for teaching colleagues or non-experts. Also, screenshots can be taken with a simple click on the corresponding symbol in the display. The localization result can be stored, recalled and post-evaluated with different zoom levels to take even more screenshots. All stored data are available in SignalShark's data logger and can transparently be accessed through its Windows 10 directory too. From here, data can easily be exported to a USB drive or SD card. Last but not least, another SignalShark highlight: it is even possible to create report files with screenshots and power level logs automatically based on SignalShark's Python script capabilities. This again saves time and maintains working quality. In our video we have seen that the sources of external interference in mobile cellular networks can be numerous. In the Operation Maintenance Center, OMC, network operators can get aware of interference based on key performance indicators, also called counters, such as the Call Setup Success Rate (CSSR) or the Traffic Channel Drop Rate. Based on comparing such counters at surrounding base stations, the interference source can even be coarsely located, providing interference hunters an initial starting point. Once the interference hunt has started, we have to overcome various challenges throughout various hunting phases. Detecting and usefully analyzing the interference may take a significant amount of time and can be optimized with a powerful real-time spectrum analyzer as SignalShark. While driving too, we are challenged by difficult reception conditions such as reflections. Using a modular and automatic direction finding system as SignalShark with its magnetic mounting plate provides enormous advantages, since it can be used on any car and it takes hundreds of 3D bearings until we are provided with a heat map and a localization result. Throughout and after our interference hunt, we occasionally experience a lack of a helping hand or someone to consult with. Writing a report on our findings means additional time effort. With SignalShark we set the basis to overcome these challenges, as SignalShark can be operated remotely by means of an LTE stick in a remote desktop session, and it can incorporate with a navigation system too. Moreover, it can generate report files automatically based on Python scripts, And based on SignalShark's Windows 10 environment, users have a great set of tools for display recording and simple data exchange. All these aspects make SignalShark a great helper in a challenging environment and allowing us to perform better in shorter time.
SignalShark, 7 senses for signals.